Okay, so you'll see your book or your professor maybe represent this compound like this. A C bonded to 3 oxygens. Each of the oxygens will have a partial negative charge on them, and there's these 3 dotted lines in between each of the oxygens and the carbons. Okay, so hey, this is known as a resonance hybrid, and if you want, I can write this down. This is known as a resonance hybrid. Okay? So it's called a resonance hybrid because, hey, it's a hybrid. It's a mixture of 3 resonance structures that we drew out here. Notice that none of these oxygens have a full negative charge on them. However, they all have partial negative charges on them, right? Indicating that they all have the same charge. No oxygen is different from any other, right? And you should also notice that none of these oxygens has a double bond. Instead, you will see that each oxygen is single bonded, right? And has these little rows of dots in between it and the carbon, which I've designated in blue, right? And hey, no, these dots don't represent a bunch of electrons between the carbon and the oxygens. These are dotted lines representing that a double bond sort of exists here, sort of exists here, sort of exists here, okay, but sort of doesn't at the same time. If there was actually a double bond there, we would have drawn a solid line, or a solid line, or a solid line, right, you guys? But hey, it's not a full double bond there, so we just draw these dotted lines, indicating that there is sort of a double bond there. There is some double bond character there, okay? Because experimental evidence tells us that each of these oxygens has the same bond length, and so we drew these dotted lines to indicate that there is some double bond character there, but not completely between any of the carbons and the oxygens, right? And that's an example of a resonance hybrid, you guys. But we hardly use these because they are a lot messier than drawing out separate resonance structures like we did before. And you may not see it now, but it would be really hard to deal with these resonance hybrids in reaction mechanisms, which we're going to see later on. So hey, mainly just concentrate on drawing these resonance structures. I just wanted to show you this resonance hybrid so that you know what your book or professor is talking about if they presented it like this, okay? Make no mistake, you guys, resonance structures aren't a 100% accurate way of representing these compounds, but it's the closest thing that we've got, okay? So I want to point out a couple more things here before I show you how to actually draw these things, how to draw resonance structures, okay? Alright, so the first is to note that there are brackets around this set. Whenever you have resonance structures, you always include them in brackets to show that they belong in a set, okay? These structures are inaccurate when taken alone, so these brackets ensure that you always include them as a set, okay? Alright, so the second thing to point out here are these double-headed arrows that you see connecting these resonance structures. And write this down because I want to make sure you don't get confused about this. Note, double-headed resonance arrows do not equal equilibrium arrows. These do not equal equilibrium arrows. Okay, which look like this. Because remember, you guys, in equilibrium, you have compound A, and it turns into compound B, and they interconvert between each other like that, okay? A reaction is occurring between A and B. Atoms are being rearranged as you go from A to B and B to A. But this is not what's going on with resonance structures. No reaction is occurring between these resonance structures. No atoms are being rearranged, okay? The only thing that's moving is electrons. I'll say it again. In resonance structures, the only thing moving is electrons. You are making and breaking bonds by moving electrons, but no atoms are actually being moved, okay? And this may sound weird, because I know that I told you before that a reaction is occurring whenever you make or break a bond. So just so you don't think I'm a hypocrite about that, let me add one thing to that definition. So a reaction is whenever you make or break a bond which causes atoms to change positions. In order for it to be considered a reaction, atoms have to change positions, all right? And check it out, you guys. None of these atoms in these resonance structures changes positions. These structures are not interconverting between each other. These are just three drawings trying to represent one compound, okay? And I know this is kind of a weird concept, okay? It sounded funky to me when I first heard it, right? But if you can imagine it, this compound is all these structures simultaneously, okay? So CO3 2-, this compound is all three of these structures simultaneously, which is what the resonance hybrid was trying to demonstrate as well. Alright, so what this means is, you guys, these oxygens that you see up here don't actually take turns having the full negative charge on them like these resonance structures imply. They each have a partial negative charge on them all the time, okay? So, hey, there's always a partial negative charge on this oxygen, always a partial negative on this oxygen, always a partial negative on this oxygen. They're not actually taking turns having this negative charge on them, okay? And this can be seen more clearly with the resonance hybrid, okay? We just draw it like this for the sake of clarity, which you'll see later when we get to reaction mechanisms, all right? But for now, when you're drawing resonance structures, just remember, you guys, the only thing that's changing in resonance structures is the position of electrons, okay? So, hey, these are the ideas behind resonance. I hope that at least made the logic behind resonance structures a little clearer. Now let me show you how to draw these things, though. Alright, so drawing resonance structures for the first time may be a little difficult, okay? But if you practice, it'll be no sweat, alright? So, hey, there's three basic rules you always must follow. Let's write these down. Three basic rules, okay? And the first one is, atoms do not move in resonance structures. Atoms don't move. And this is followed up by only electrons move in resonance structures, okay? So number two, so atoms don't move, only electrons move. Only electrons move. But make a note here, you guys, because you can't just go around moving any electrons you want, okay? So, hey, note, that was like an asterisk, okay? So, hey, note, you can only can move electrons that are in lone pairs or multiple bonds. So you can only move electrons in lone pairs or multiple bonds. Okay, you can never move electrons that are in single bonds. Okay, so you can only move electrons in lone pairs or multiple bonds, but never, not electrons in single bonds. Never move electrons in single bonds. That's a big resonance no-no, okay? All right, and the third basic rule for resonance is that some resonance structures are better than others. Okay, so, hey, some resonance structures, and let me go ahead and erase this, just realize you can only move electrons in lone pairs and multiple bonds, never those in single bonds, okay? So the third rule was saying some resonance structures are better, and next to better, write in parentheses, better equals more stable. Okay, so some resonance structures are better, which means more stable than others, than other resonance structures, okay? And these better, more stable resonance structures are known as major resonance structures. Okay, so the better, more stable resonance structures, these are known as major resonance structures. And so the worse, I guess you would say less stable resonance structures, these are known as minor resonance structures, or they're also called major or minor contributors. Okay, so the major contributors, these are the better, more stable resonance structures. The minor contributors are the worse, less stable resonance structures, okay? So knowing that there are more stable and less stable resonance structures, let me tell you that there are 4 factors of stability. Most of them which are really common sense, but let's write them down anyways, okay? So, hey, how you can tell what's a major or a minor contributor, what's a more stable or less stable contributor, we have 4 factors, okay? 4 factors. And the first factor of stability is separation of charge. Separation of charge. Okay, well, as a general rule, you guys know that the less charges, the better, right? And by better, I mean more stable. Okay, well, what this rule is saying, separation of charge, is that if you have to have charges in your compound, make it so that the like charges are as far apart as possible, so that they are separated as much as possible. And this is common sense, right, you guys? Because you don't want to be putting a negative right next to another negative, right? What would happen? They'd constantly be repelling and complaining about being next to each other. And that's bad, you guys. That's like having 2 kids in the backseat that don't like each other, right? Very, very unstable. Get those kids as far apart from each other as possible. Likewise, get like charges as far away from each other as possible. Separate them. And hey, the inverse to this rule is put opposite charges next to each other, because opposite charges can cancel each other out. Take-home messages: separate like charges, okay? All right, so the second factor of stability is even more common sense. Let's write this down. And the second factor of stability is that octets are stable. Okay, so hey, octets equals stable. So if an atom has an octet, hey, it's more stable than an atom that doesn't have an octet. Duh. Having a filled octet is more stable than not having one, right? All atoms want an octet. Okay, so, hey, common sense. Let's move on to the next factor. And the third factor is to put the negative charge on the most electronegative atom. Okay, so if you have to have a charge in your compound, put the negative on the most electronegative atom. So put the negative on the most electronegative, and I'm going to abbreviate this EN, okay? Put the negative charge on the most electronegative atom. And this makes sense, right, you guys? Because which atom is going to have the negative charge on it most likely? Is it going to be the one who's really electronegative and pulling really hard on those negatively charged electrons? Or the atom who's not very electronegative, who's not very eager to get those electrons? The really electronegative atom should have the negative on it, right, you guys? Because he's pulling those negatively charged electrons towards himself. And hey, the inverse to this rule, of course, is put the positive charge, if you have a positive charge in your compound, put it on the least electronegative atom. Okay, so hey, put the negative on the most electronegative atom. If you have a positive charge, put the positive charge on the least electronegative atom. Okay? All right, so that was the third factor. Let's get to the fourth factor.